Okay. We're starting. We're starting, people. People, we're starting.
Yes.
Yes, good. Thank you. Excellent. Lovely. Good. So when we looked at that, when we looked at this algorithm, the only thing that we haven't talked about is what is the complexity? What's the complexity of the algorithm here? And the answer is very clearly, wow.
Heard someone yell N on who it was.
Yeah. Now, the thing is like this. When we come to recursive functions, to be able to compute the complexity, it's a big story. It's not so simple. In the next data structure course, and next year's course, you'll be learning what's called master theorem, which is you'll be learning the actual formal way of computing the complexity of a recursive function. What we'll be doing in this course is really more along the lines of intuitively looking at recursive algorithms. Because, okay, look, this is O of n, this is n squared, but not with any type of really big formal proof, because to do a formal proof, you need to know the actual runtime function, the T of n, the runtime function, and with the recursive function, it becomes a bit more, not as simple. So basically, in this case, it's theta of n. We're running n times. Each time we're doing here constant pulot. How many times are we doing this constant pula? The constant commands. We're doing that n times. So it's n minus 1 and plus n minus 2 plus n minus 3, all that, which basically comes out to be, n. Okay, so that is that. Now, let's take a look. Let's take a look at this question. Now, this is a question or similar question that you might have done in the Intro to Computer Science course with a loop. Because again, what's recursion? Recursion gives me the opportunity, the capability to do loops. That's for sure, that's what it gives me. So, okay. It gives me the opportunity to do loops. This is a loop inside a loop even. And this could be another question at the level of Intro to Computer Science. But here you're asked to do it as a recursive function. Okay. How do you do it? How do you go about doing that? The question to everybody: have you done in any of your courses? Have you used breakout rooms yet?
What was it? I don't.
Have you used in any of your courses breakout rooms in Zoom?
No.
No.
Nope.
Good. We're gonna have fun then. Okay. Yeah, we can do it now. What I'm going to do now is I'm going to put you all in what's called breakout rooms. I'm going to put you guys in rooms of between 2 and 3 people. You have 2 to 3 people in the room. You'll see on your screen to join a room, and you can work together solving the problem. Okay? I'll be walking around between the rooms, between the groups, and I can talk to you about the question itself as well. And I'll give you a warning when we're going to come back to the whole classroom. So let me just see, make sure that everybody's in the room at least now. So I have to, let's say, exchange him to room 7.
You do it with like recursive, I mean, one function calls another function?
Yes, that's what it looks like. Yes. Sorry, 1 minute. Okay, everybody has 3. You have either 2 or 3 people in each room. And I'm opening rooms now. So everybody now got an invitation to join a room. So please join your rooms now. Amitai. Yofi, good. Yuda, you haven't joined the room yet. Simcha's all by himself. There should be, Yofi, there's more people in your room now. Good. Okay. You can talk to each other.
Hey, the breakout room crashed and then everyone in the room was gone.
Simcha, you could try to join in again. And whoever AP is, you haven't joined in yet. Oh.
My Zoom is very messed up. I can't join any of the room.
Okay, I'm going to send you to a different room.
And Professor, my Zoom crashed on my computer when we went into the breakout room, so I just switched to my phone.
All right. Let's stay there.
There we go.
Hey,
Oh, Professor.
I can walk around.
Yes, we can't see the problem.
Oh, you can't see the question. Oh, yeah.
I don't think anybody can.
Ooh.
Let's talk about the real question. As soon as you
Yes.
did the breakout groups, Professor, I was like,
Yeah.
wow, Zoom stock might actually be worth something. So I
You
didn't
know,
know.
the breakout rooms are really great, and I've used it. I've used it with quite a few groups already, and you should be able to see you can't see the question?
We don't see it. That was our issue.
Where are we supposed to look?
You should be able to see it on your thing. Okay, you're not the only guys who are asking. 1 minute. Double check now. Yeah, you have a problem seeing the question probably, right?
Yeah, no, I can't figure out what the question is.
Yeah, I know. Everybody's having a problem for some reason. I don't know why. Okay, I'm going to close all the rooms now.
Is this the breakout room? Is this the breakout room? I can't hear you.
Yeah, now you can. No,
Okay.
we're back into the main groups because
Got it.
you can't see the question. So instead of wasting our time, I'm going to now...
Wait, if you just put up the question, give us like a minute warning, then we copy it down and then go to breakout rooms.
Yeah, but that's chaval. Okay, let's just
We can
now...
take pictures with our phone.
Nah, chaval on the time. Let's just do it this way and finished. Okay, so you got a question. And you have to still solve it, though.
I don't think everyone is back.
Yeah, everybody's coming back slowly. People are coming back. People are coming back. Hey. Hello, Jonathan. Wait, everybody's turning off their cameras. Oh. Okay, so if for some reason I did hear from some other lecturers that the breakout rooms were causing some type of problems a bit. I've used them so far very nicely. I'll have to figure out why you couldn't see the screen this time. Okay, anyway.
Because you were screen sharing only with the original room. It doesn't transfer.
There is a way that it does, because I've done it already.
Wait, why do we need to see the original screen?
You want to see the question?
So if everyone writes down the question and then goes.
Yeah, I realize. Okay, but it's on the time right now. All right, so meanwhile, back at the ranch, people are trying to figure out how to answer this question.
We still can't see the question.
Why
You
not?
share the screen.
You're not seeing it? Oh, sorry. No. I thought you guys are seeing it. Huh. Mm-hmm. Sorry. Here I'm talking, thinking that you're seeing the screen. How about now?
Yeah.
Yeah, back again. Great. Okay, so you're going back to work on the question, please.
Are we supposed to know what X is?
Yeah, you'd have to input X and a K if you want to have.
X is a parameter.
Because it just seems to be saying the function accepts
K
it.
Very correct. The question is not written correctly. And
We're doing it in pseudocode. Why can't you return whatever, just as a messy number?
Okay, two things. One, it could be when I translated to English, I forgot to add that it also accepts X. Should also, yeah. The function, that's the function, it gets X and a K. Okay? I'll have to fix that in the slide. What slide number? 4.
Like our group figured that out, that you have to have two.
Yeah, you have to have two. Okay, I'll fix the slide and I'll update it in the Moodle site as well, but okay. It accepts K and X. Now, where's the recursion here? So I'm going to talk out loud. I'm going to think out loud. How do I go to write a recursive function for this type of thing? So basically, I want to see what is my general case and what is my base case. Those are the types of things. When do I finish this? Basically, when K is equal to 1. If K is equal to 1, what do I want to return? I want to return 1 divided by X. Right? If K is equal to 1, right? X to the K, X to the 1. Okay, just return this and we're finished. And if K is equal to 2, K is equal to 2, I want to return, what do I want to return? I want to return this minus this. And if K is equal to 3, I want to return this plus what I had beforehand. 4 is this, with all what I had beforehand minus that. K, depending if it's, depending, what an interesting word, depending. It depends. If K is odd or even. If K is odd, I want to add this to everybody beforehand. And if it's even, what do I want to do? I want to subtract it from everything beforehand. What is everything beforehand? If it was odd, so it's this plus everything beforehand. All the way back until I get to K is equal to 1.
So you want to start from the end?
That's for the base case, yes. So basically, I just talked to myself, and everybody listened, actually. I thought out loud. I wanted to show you a bit how I went about trying to solve the question. Okay, so let's take a looky. If k is less than 1 or x is less than 1, return error. Now, what's it say here? It accepts a natural number and return and x. And here we're saying if k is less than 1 or x, then return error. Now, what's return error? But the function returns a number. You're going to say, how can my function sometimes return a string and sometimes return a number? You can't have both. And the answer is very clearly you can. This is pseudocode. Pseudocode, everything goes. I can say return error, or return error, return a number, return a number. When I go now to implement it in C++, I have to think how to do it. So in C++, you've already gotten, I think, yeah, you've probably got 2 exceptions already, right? You've learned exceptions?
Yeah, we have.
Right, so here it would be, if I'm going into C++, I'll say then throw, some type of exception. That's how I would implement it. But again, in pseudocode, I don't have to worry about how I'm going to implement it. I'm saying, look, you have to return an error. How I'll do it, I'll send a value like this, or I'll do this, or whatever, right? I'll blow up the computer. I don't know what. In very simple Hebrew, we'll say machpatli. Well, what's the difference? Return error. In C++, or in Java, in C#, I'll throw an exception. Not every language has exceptions. I'll do it a different way, whatever. That's one of the reasons I brought the questions, because of that business, return error. Now, if k is equal to 1, this will be my base case. Then I want to return 1 divided by x. That's what I want to do, 1 divided by x. And if not, remember that word I said, depending. Depending means it will be a if. Wow, welcome to pseudocode. If even k. Even, what is even? That's a function. I made it up just now. Now I could say if k %2 is equal to, or mod 2 is equal to 0, then. But I just wanted to show you, everybody that saw it understood what we're talking about. Actually, maybe even could be another connotation in English. I could say if odd. Then you understand what it's doing. I don't even have to implement it. If k is even, then what I want to return? I want to return, what do we say? If it's even, for example, here. If it's even, I want to return everybody before that minus this value. I bring to your attention this sign, and I think in English it's called a caret, C-A-R-E-T. It's used to represent a subscript. It's like writing x to the power of k. In a lot of documentation, in a lot of places you'll see this. Actually, there are some languages, that's how you write to the power of. In C++, we have the function called pow. But in some languages, you can do star, right? X star 2 is x squared. And there are languages that permit it's x to caret k, but it means x to the power of k. That's what we're returning. We're returning this minus that. And if not, return that plus that. Now this is not this is not multi-recursion. It's not multiple recursion, because he only goes here or here. He doesn't go to both. And by the way, else you spell without an E, without extra E. Like that. Also, else. I'll fix that as well. Okay. Else return that. Okay. And that's the whole function. Questions? Anybody have questions on that? Menachem Mendel, you have a question?
No, I did it like this.
Okay. No, because I saw that you raised your hand. Could be from a long time ago. Okay.
Oh, yes.
Okay, good. Tough. here's another question. Oh, sorry. I wanted to ask you, what is the complexity? What's the complexity here of the function?
N.
N. Theta shell or O shell, N. Okay, who said that? Who suggests N?
I think it was Yitzchak, but we saw it. But why?
Okay.
Why? Can you explain again, please, how you figure the if it's recursive?
The what?
How do one go think through that if it's recursive?
Okay. First of all, let's just see what it is. First of all, how many times are we going to do this? We're going to go into the recursive function. How many times?
K times.
K times. It's linear, but there's no N in this question. There is no N. It's K. It's a function of K, right? K number of times I'm going to go into and do this evaluation. We're going to go here, K times. That's what I'm going to do, right? That's what I'm going to do. I'm going to do it K times. And therefore, intuitively, I can say, okay, it's K times. What am I doing each time? Each time I'm doing a constant time, some type of calculation that runs in constant time. So I'm going to do K, K times this constant. So K times a constant is K.
It's not like this, like a series of like, you know, K down to.
Yeah, but no, in this case not, because it's not 1 plus 2 plus 3 plus 4. Because each time what I'm doing, I'm only doing a constant amount of operations. The calculation I'm doing in a constant time. How many times am I doing that? I'm doing it K times.
Each of those K has to call the function.
Yeah, but that's the K times. That's the loop. Think about it differently. If it said here 4 I is equal to 1 to K, you'd agree with me that means that the runtime is K, correct?
Right.
So the same thing here. The recursive call is that gives me the manganon, gives me the capability for the loop. Recursive call is the loop here. And each time K is one less. But it's not a series. Okay or not?
I'll think about it more.
Okay. Hafoch ba ki kulo ba. That we learned in the Mishnah. Okay, next question. Last one. Last question. Wow. Interesting question.
Will that answer?
You have an answer already? Great.
I mean, not written, but like to explain.
Okay, let's hear your kivun.
Well, it seems like every time you only need to check the base case when there's only 2 numbers left, then you see is that bigger than the previous one. If it's bigger, then you can return 1. If it's smaller, then you can return 0. Then for every other one, you return 1 times the previous one. So if the previous one was wrong, then it'll be times 0. So therefore, all the ones after that will also return 0. But otherwise, until it finds a false case, it will continue returning 1 times 1.
Okay, that's cute. You can also use the OR function, by the way. Why multiply? You can say it's this or this.
Yeah. Mm-hmm.
Right? That's a cute way of doing it. And we'll be using that type of mechanism a lot, even next week a lot. But if you want a value, a true or false value, to sort of ripple up, you can use and or for it to ripple up. If you want it, if it's enough one time that it was 1, then you can just do an or. In this case, you want, if already you found one time that there's a psila that's no good, so you can do an and. And that and, once I do an and with a 0 or a false, that will ripple up, makes no difference what everybody else is. If everything else is hunky-dory. But one time it was false, if I do this and this, that false will ripple up all the way to the top. Cute. But the same idea like you said with the, because it's 1 and 0, you can also do a multiplication. Same idea. Excellent. I'm going to make the question a bit more complicated. And I'm going to say that you need to also make another function to sum up all the values. A recursive function to sum up all the values. You know what? I'll give it to you. Here is a function called sum. It receives an array, an n. If n is equal to 0, return 0. And if not, return the sum of a n plus the sum of n minus 1 numbers in the array. So what do I get here? It's going to return to me the sum of the first n elements in the array. If you have this function, it will help you write the function in the question. So instead of doing a loop inside your function to sum all the previous numbers, I'm giving you a function called sum, which happens to be recursive. Say that, it happens to be recursive, that's fine. It's not a problem. You're allowed to do that. All right, so how does it work? I'll give you another minute or two to start thinking how to write an answer. Think about it. Anybody have a suggestion?
I have like part of the suggestion.
Okay, let's hear.
First, you go to n to 0 all the way back. Like you call the function n times until you get 0.
Okay.
And when you got 0, you just take the first number. If the first time you don't do nothing, you just return 1. And you'll see next time you'll check if the second number is the sum of the. Before you need to create a sum outside. That's my problem. You create a sum, I use the sum function, and it's equal to 0. So you check if the sum is bigger. If the sum is bigger, you return 1. Else you return 0. So the next time you just check if it's 1. So every time you check if it's 1. If it's 0, you just go back. You go out. If it's 1, you go to the next one and you check again. If the sum is bigger, return 1. Else, return 0 and keep going.
Excellent, excellent. So let's take a look. My function gets a and n. If n is equal to 0, I'm going to return 1. 1 here means true, what we were talking about beforehand a bit. If I got here, when n is equal to 0, obviously it's true. It's bigger than its previous numbers. Now, if not, if f thing is equal to 1, if it's equal to 1, the previous n minus 1 numbers was true, and this particular one, this a and n, is greater than the sum, then return 1. But what am I returning true? 1 and 0 will be true and false. What am I returning true? If previously my checking was true, and also this particular number where I am now, a n, is greater than the sum. And if true, if yes, then return true. Else, return 0. That is my whole function. Not everybody understood, correct? Correct? Everybody understood?
I'm stuck on the base case. If
Yeah, I
any-
know. Good. Okay, so therefore, let's take a looky. Okay, my sum, in a minute, we're going to go through it. Just look at the complexity for a minute. The sum function runs in n time, obviously. It's a function of n because we're going to sum up n values in the array. And f shall a of n will be, how much? What's it going to cost me?
Also 11.
Nachon, n squared. Why n squared? Because I'm going to do this n times, right? But every time I do, for every one of these, I'm also going to do call sum. Sum costs me n. So n times, because I'm calling this function sum inside this recursive function, it's costing me n. It's like I have a loop here. If I had this as a loop, you'd say straight away it's n squared. So instead of a loop, it's a recursive function that costs me n, so it's n squared.
Why isn't it O of n squared? Why is it theta? Whether it's
Because in this case, it's theta because it's bounded also from top and from bottom by n squared. But I don't have a higher upper bound or a lower bound than n squared. It's a tight fit between in n squared, so I can write theta. You can write O as well, right?
That's what I'm asking. In other words, if theoretically you could return false, right? You could have a huge list, and the sum still was theta of n. But in the greater function, you need to you like as you were explaining to before. If once something is false, even if it's everything else is hunky dory, it's over. So,
No, it's not. That's the thing. It's not like in C++ where in this case, he's going to have to do, he does everything. It's just going to float up. You know what? I heard your question. Let's take a look together. Take a look here. Here's our function, okay? And here's my array A. Okay, small array so we can see it. So what are we doing? I'm going to call the function A5. 5 is n because I have 5 values. So basically my call f of A5 says the following. N is equal to 0? No. So if the f of A4 is equal to 1 and A5 is greater than the sum of A4, then I'll return 1 or 0. Okay. But to be able to evaluate this, I have to figure out first, even before I get to this, I have to check this. Is the FA of A4 is equal to 1 or not? Oh, okay. Let's take away. Wait a minute. What is f of A4? F of A4 is the f of A3 is equal to 1, and A4 is greater than the sum of A, 3, right? If I have this answer, I can return it to him. Come on. If this is true or false, I'll return 1 or 0 here, and he'll get the value. I'll say, okay, let's figure out what this is. What's the f of A3? It's the A2. I'll figure out this and return you a value. But 1 minute, wait, just A2 is A1. Or what's A1? A1 is if f shall A0 is equal to 1. Okay. Now what is A0? If n is 0, this is my base case, and this is the answer to both questions beforehand. If n is, then it returns 1. he's going to return 1 now. Who's he returning 1 to? He's returning 1 to here. Is 1 equal to 1? Yes, that's true. And is A1 greater than the sum of A0? Yes. It's greater than the sum because it's only one value. It's greater. So I'm asking basically, is 1 equal to 1? And is 3 greater than 0? Yes, it is. So the whole, this condition is true and true. What am I going to return? I'm returning 1 to who? To the person that asked me. He asked me, tell me, are you true or false? Ah, you're true. Ah, so nice. So is this true? And is A2 greater than the sum of A1? What's that mean? Is 6 greater than the sum of all the previous ones? The previous ones is 3. Oh, you're both Yofi, hunky-dory, as we said, Yofi. So A2 we know is equal to 1. So is that equal to 1? And 10, is it greater than the previous values? Yes, 10 is greater than 9. So we can return also a 1. And now here, is this greater than A3? And you understand why I had to do this? Because we're not in the classroom, I can do it on a board. I had to do all this for you guys. Now, 20, is it greater than 19? Yes. Ooh, Yofi. So, 4 was equal to 1. And A5 is greater than, 45 is greater than 39? Yes. So, we're going to return 1. No. Questions?
So this is, I don't know, not really a question, but I think it's pretty inefficient to do an O of n squared for such a simple thing. If we want, you could just add a third variable when call a function, which is the sum. And if you do it like that, then it'll.
Okay. The thing is like
this. 0.
Okay.
Add 3 and then return, and
okay.
it would save.
Okay, I hear what you're saying. Look, that's one of the big things with recursion. A lot of times I can have some type of static variable, let's say in C++. I'll define something as static, and then it would be fantastic. I'll define a static variable which has the sum all the time. Matov. And the question itself was defined that you only get the array and the number of values in the array, the size of it. You're not allowed to include additional variables. But you're correct in that, but it's sort of breaking the concept of the recursion, because you want the recursion to be self-contained. So you can set another variable. Yes, it does happen. I'm not saying no, but it's not preferable. Jonathan, you have a question?
Yeah. So in this case was I see where it worked out that it was n squared exactly, but in the second set of data that you had in the previous slide, when the answer was false, it would have gotten stuck by 70, and it wouldn't have run through the whole function another n. So why
yes, it would have. Sorry, yes, it would. Because what happens? Let's say here. Let's say we're here. And A4 isn't greater than the sum of A3, so then it will return a 0. So A4 won't be equal to 1, it will be equal to 0. So basically that 0, because it's an AND function, if one time somewhere here I returned a 0 instead of a 1, that 0 is going to ripple all the way up because it's an AND function. Okay, Jonathan?
You're right, I see. Wouldn't there be a way to write it that it just comes out of the loop, the whole?
So, exactly, this is the problem. We're not in a loop. You don't have a break function. We're not in a loop, we're in a recursion. So one way you can do, which is not nice, and you don't want to do it because you'll have a lot of memory issues, because don't forget, when you're doing a recursive function, it throws all sorts of things on the stack, and when you're returning from recursive things, it unrolls from the stack. I can throw an exception. but then I have to start clearing up the stack, and it's a lot of work. I'll have a lot of problems with my internals if I throw an exception through that recursive function.
Didn't you kind of do that by the return error and the
Yeah, I
previous
know.
example?
No, I said that. You have to know how to do it. Definitely. I'm not saying that you can't, but you have to think how to do it in a smart way. No,
Professor, where it comes out, we're saying that every recursive function is going to be a theta, not an O. Unless you...
no. I'll be showing you in a couple of minutes a function that doesn't answer that criteria, a recursive function. You'll be seeing that soon. Okay? Okay. This is nice. If you didn't chop it to the end, you can go through it, one stage after a stage, go through it. It's not that sure.
A small code question. Do we assume there's an end? Is it like lazy evaluation? So only if the first one, then don't check even the second one? Like, how do we think about it?
Again, I didn't understand.
Lazy evaluation, meaning you look only at the first half, and if it's a 0, then don't look at the second half.
Okay, well, that's the thing. That we're used to. We're spoiled with the optimization of a compiler. In C++, we know, for example, if you have an and if the first term is false, it doesn't even go to the second term because that's a way of the compiler's more optimized. That's called optimization in the compiler. But at the algorithmic level, we have the and here. Yeah?
So you do both?
Yeah. It does. Okay. Both get executed in this case. Now you could theoretically separate the if to 2 parts and then do a return 0 and not go in. Yes, I could change the code a bit to basically to implement that optimization. But what I could do is if it's equal to 0, then I can already return a 0 and not go into this part. I could change this. If it's equal to 0, return 0. Else, if an is greater than n, then return. I can divide this into 2 parts. But again, it's still you're right. I'm optimizing, but it's still going to be the same complexity in the end result. Okay.
All right.
Good. Now, are you ready? We're going to spend now the next few minutes, quite a few minutes. We're going to be talking about quicksort. Now, quicksort, Rabbi say, is quick. No, it's a lovely sort. It's used a lot. It's a very common one. In C++, you'll be learning STL. You haven't got to that yet, I think. You'll be getting to that in a couple of weeks maybe. And you'll see there's built-in containers, there's built-in data structures with algorithms. You'll have a command called sort. A function called sort, you don't have to write it even. You can just use it. The sort behind, the algorithm behind that sort, if I'm not mistaken, in C++, it's a quicksort. Quicksort is a very popular, very, very popular sorting method. And it's nice, it's good, it's efficient. And let's start understanding how it works. Quicksort works in the following way. We receive the array and P and R, the 2 upper bound and lower bound. If P is less than R, Q is equal to partition APR. Quicksort A, PQ minus 1, quicksort. One minute. This looks familiar. It's different, but familiar. That's what you're thinking to yourself. It looks like a merge sort, But merge sort worked dafka biduk opposite. We had merge sort, and then merge. Right? We said, okay, do a merge sort on left hand, right hand, and then merge them together. Here, we're doing something like this. We're calling some type of function called partition. Don't know what that does. That returns to me an index. Let's take a look. Here's a function. That's P, and that's R. P is less than R, yes? Q is equal to partition APR. After I come back from that function, partition, Q, he returns to me this value, the index of this tab. Who can tell me or guess what partition does? What does partition do? Besides returning Q, the index Q.
It takes the R and puts it randomly in the data set.
Nope.
I know, but it's because I watched a lot of European dances. So
okay, so let's give other people a break. Okay.
Is there any way we could backtrack a little? I lost you a little bit at the beginning.
Basically, I'm saying I went to this function called partition. And after I came back from partition, Q is pointing to this, this element. And this is what my array looks like after I came back from partition. My question is, what does partition do?
It looks like it takes the last number in the array and moves it to where it's going to be its rightful place.
Correct. That is half the answer. You are very correct. You would get a wrapper of a candy because you didn't give me the full answer.
Do those like add up to candy eventually?
Yeah, why not? I have a lot of chayvais. When we do physically meet, I'm going to have to give out a lot of candies to you guys. Okay, yes. Talk to me. What else does it do? What you said was correct, but not the whole story. I'll repeat what was said. What was said, that it puts the 28 in its place, where it should be in the end result. Correct. But it does something else. Look carefully. What else happens?
Puts the max number between that and the previous number at the end instead?
Nope. Because actually, in this case, 36 is the next one. And
No, just between the one, between it and the one on its left.
Nah, that's Bimikre. And okay, who said that?
It's right position.
Simcha? What are you saying?
In its right position.
Getting closer. You're a bit warmer. Take a look. What's on the left-hand side of the 28? What's on the right-hand side of the 28? What's special?
Everything that's less than 28 and everything is more than 28 is on the right hand side and the left hand side.
Exactly. Take a look. What happened is that we put 28 in its place, but also something else. This partition algorithm, it's a fancy algorithm. And what does it do? It makes sure that all the numbers less than 28 are here, and all the values above 28 are here. And Q is in its place. So basically we're saying partition. Divide it up. Take 2, and now do a quick sort. Who do you do a quick sort? From P to Q minus 1, because Q is in its place. And then please, after you finish that, do a quick sort on the other half, from Q plus 1 to R. Lovely. Isn't that lovely? It's like,
Again.
Basically, this partition, which is not recursive at all, partition says, look, take this array take the last number in the array that I'm dealing with and put it in its place where it should be, and make sure while you're doing that, that all the numbers, make sure that all the numbers which are less than 28 put here, and all the numbers that are greater than 28 put here. That's what the partition does. And after I do that, I'll say, okay, thank you very much. You partitioned it to me. And now I'll do a quick sort on this part. What's this part? It's from P to Q minus 1, right? So P is P, and when I do the recursive call, my R will be Q minus 1. This will be the P, and this will be the R. After you finish doing this whole sort, then sort this way. Now, what am I saying? Sort it with quick sort. If you want to write here bubble sort, but then it won't be efficient. I want to use the same sorting method. Okay, so what happens here? Partition, partitions. And now I want to sort the left-hand side and the right-hand side. But this doesn't have to be quick sort. You can put bubble sort here if you want. It will work. It won't be efficient because bubble sort's n squared. Okay, let's drill down a bit. So we really want to see what is partition. How does it work? Here's partition. This is partition. Theoretically in the classroom, I'd start using my PETEX, my yellow sticky notes, and do it on the board and everything, but I can't do that. So I spent a bit of time and made you the following. Not only you, also the Hebrew speakers, but let's take a look.
Thanks.
We have here an array. This is my array that we're going to play with. Here's A, this is P, and this is R. Okay? Pivot. Now, the word pivot is a very crucial word. We call the pivot in Hebrew the Evaltzir, like not in basketball, it's a pivot. It means the pivot value will be the value from what I work with left and right, the pivot, right? So pivot is equal to AR. So here's pivot, right? I have my thing called pivot. It has the value 28. I is equal to P minus 1. P is equal to 1, right? Because our arrays, we call the indexing start from 1 and not from 0. We're not in C++. So I will be, in the first case, 0. I is pointing to a non-existent thing. For j is equal to P to R minus 1, I'm going now to go through this whole array, step after step, until here, until R minus 1, because that's my pivot value. I don't have to deal with him. I want to check who's bigger or smaller than this 28. Okay, so my j will start now. J is 1, right? P to R minus 1. Now I'm going to ask a question. Is AJ less than or equal to the pivot? Who's AJ? 14. Look at this. AJ is 14. Is he less than the pivot? 14 is less than the pivot? Yes. So what do I do? I is equal to I plus 1. I plus plus. So now I is equal to that. Swap AI with AJ. Oop, yeah. What am I doing now? What am I swapping? Somebody help me?
A number that's smaller. Never mind.
Okay. Somebody else want to help me? What am I doing? I'm going gornished. I'm swapping him with himself. Swap AI. AI. This is AI. And this is also AJ. I with J is equal to 1. Swap him with himself. Okay. I'll swap myself. You're going to say, not very efficient algorithm. Swap him with himself. Okay, let's see what happens. J now is equal to 2. Right? J is now this value. Is AJ less than the pivot? No. So what do I do now? I is equal to I plus 1. And we already know what's going to happen. Swap AI with AJ. It's the same guys. Continue. J is equal to 3. Is 8 less than the pivot? No. So I is equal to 3. Great. Now, so solve somebody bigger than pivot. J is equal to 4. Is 8j greater than the pivot, less than the pivot? No. Therefore, he doesn't go into this block. I stays the same. I didn't change I. I don't do any swap. That's it. That's all I do. AJ is not less than the pivot. AJ, this 32, AJ, this guy, is not less than 28. So don't do anything. So, okay, let's see what happens. Now, J is equal to 5. Is AJ, this is 5, right? This is 1, 2, 3, 4, 5. 17. Are you less than the pivot? Yes. Oh, okay. I is equal to I plus 1. This is I now, correct? Correct. That's I. Swap AI with AJ, and now looky. What's happening now? Swap AI. Who's AI? The 32. And who's AJ? J is this guy. Swap him. Take a look. Everybody watching? Swap them. We swapped them. Hey, Yofi. Good. Fine. Next. Is 42 less than the pivot? No. So I stays in the same place. Don't change it. Is 36 greater than the pivot? No. So I stays the same. Yofi. I finished the loop because I did to R minus 1. I did up to here including? Yes. So I finish this whole loop and I get to the next command, swap. AI plus 1 with AR. Let's take that pivot value. We want to put it in its place. Who's its place? All these, 1 minute, Menachem Mendel, 1 minute. So what happens here? All the values here up to and including the 17 are less than my pivot value. So I want to put in the I plus 1 place here, swap these two. Put the 28 here, and the 32 will go here. The 32 will go to the end here. And now I want to return, don't forget. Partition returns the index of the pivot value. I want to return 5. Correct? 1, 2, 3, 4, 5. I want to return 5. Now, I is 4. So return I plus 1. And that's where the pivot value is. And that's what's going to be returned. Okay, first Menachem Mendel and then Ariel. Yes, Menachem Mendel, your question.
My question is, if let's say when J is 6, the 42, it's a number smaller than 28, what's going to happen?
It will still work.
Going to swap like 17 with 32?
Yeah, you'll see. Play with it and you'll see that it works. It's lovely. Because basically I here tells you how many numbers are less than the pivot. So I'll swap the AI with the AJ. I'll make sure that it's still the smaller ones are there. It works lovely. Play with it, you'll see. It's lovely.
Okay.
Ariel, your question.
Yeah, so this seems to be assuming that the pivot will be like in the middle of the sequence. Is it, what if like the pivot is 1 or is the beginning or the end of the sequence, or do you figure that out beforehand?
Rega, again, I didn't understand fully your question.
How do you choose the pivot? Is the pivot just the last?
Oh, wow.
Because otherwise you could have it, if it's the first one or the last one, then it makes it much more difficult. It makes it much longer.
Great. Ariel's asking a very, very important question. How did you choose that pivot? Or the choice of the pivot is very crucial here. Very correct. And I'll be talking about that in a couple of minutes. But very, very correct. Kol hakavod. Okay. So now we know what partition does. Partition will take the end value and put it in its place. So if I'm going to do a quick sort on this, on the left hand, then this will be P and this will be R. It'll take the 17 and do a quick sort on that. Recursively. The same idea like merge sort, but afuch. We do the partition, and then we'll sort each side accordingly.
Can't this make worst case scenario for quicksort n squared?
Who said that?
Roni.
Excellent. Let the mortals. We'll talk to the mortals in a couple of minutes. Aval. Very good. Okay. Sorry, I was just talking to Ronnie privately. Yes. Okay. So let's take a look. You have here a link again to the visual algo. Maybe we'll go there in a minute. You have here a link to another film of the dancing. Here, definitely speed it up, because until they get there, until it works, I mean, every time that they're swapping and everything, it takes time for them to swap. So you can definitely speed up the playlist. Now, I want to show you an animation. Take a look at this. Okay, it's going to start now. Boom. This is the pivot 31. And look what happens now. There's a low and there's a high. And they're sort of coming together. We're doing the same srika. We're going through all the values of the array, but it's doing it in a bit of a different way, where we have the highest value and the lowest value.
It's like bubble sort, right?
It's a similar type of idea. And then basically, it's another way of partitioning. It's another algorithm to partition. But the same idea with the pivot is the last value in the array. But again, you can do that. It still works. But at the same time, if I'm already doing it, I'll check both sides. I'll have a low and a high and doing swaps. From the point of view of efficiency, and in the order of magnitude, it's the same thing. It's a different type of algorithm for partitioning. Bichlal, you'll see that there are quite a few different ways to partition, and we'll be talking about the pivots in a minute as well, but there are different ways of doing it. Again, you have here the is it open? Did I close it? Might have closed it. But I don't see this. A minute. Let's just go to the visual algo as well. I'll share it in a minute once it loads up. Quick sort. Let's take a look. Where are we? No, not that one. Yeah. Okay, so now I went to the visual algo place, and I went to quick sort. So again, I can just run it, and you can actually see how it works visually, and play with it, and da-da. Here, just derech agav, the pivot value, I think, was the left-hand side, not the right-hand side. No, sorry, it was the right-hand side. It was the right-hand side. Now let's see how it works. And then you have here the algorithm, you can play with it, but what's nice about it is that you can create a random list, you can create a sorted list. And this is what Ronnie was talking about. You know, what happens if it's all sorted decreasingly or increasing, or it's nearly sorted? What happens? How does it work? And you can really play around with this a lot. And I suggest to you, if you really want to start understanding a bit how it works, you can go through this and play with it very nicely. And if already we are here, I want to go here to our ESP site, and I'm going to share, stop share, and I'm going to share now. C++. Okay. So now I went to the Moodle site. So here you have the link to that site I talked about. Here you have that merging two ordered lists to a third list, which is also very, very nice. That's just a merge. Now, if I go down to our area, oops, I didn't put it yet. I put it in the Hebrew speakers, but I didn't put it the. So let me just make a duplicate and run it down to our area. What I'm going to put now into our area here we are, general materials, let's put it here. You have here the quicksort algorithms. Here is the algorithms. This is what you had in the slides. Here's the quicksort with the partition that we saw. I also gave you here the other version of partitioning using that high and low business with the I and J, like you saw in that animation. So this is the algorithm that is with that animation that you saw with the low and the high and whatever. But again, it's another way of doing the partition. Also deliberately gave you this type of pseudocode where it doesn't say equal to, it says like this, or exchange. Instead of saying swap, exchange this and this. But you can understand it. When you see it, you understand what's going on. So you have these algorithms here for you. By the way, I don't know exactly how the final is going to be, actually, but if up to now with the final exam, definitely what we have, you have a note sheet. You have all the notes, the Daf Nuschaot.
Formula.
What?
The formula sheet.
Formula sheet. So you're given the quicksort, by the way. You don't have to remember it. Balpeh. You don't have to remember it. Okay. Let's continue for a minute with this quicksort. Okay, so we have here the quicksort. What is the complexity? What is the complexity of our quicksort? Anybody have an idea?
N log n.
N log n. Why?
Because the partition is linear, and then the quicksort itself is log n.
Lovely. How many times am I going to do this partition? Log n. Yeah? Log n? You sure?
Roni said n. He said quicksort was log n.
I don't know. I hear machlekes. Am I going to do this log n? Where do I see divided by 2 here? I see divided by 2. What's log n? We said log is when we're dividing by 2. Where did you see dividing by 2 here? Did anybody see the dividing by 2 in this algorithm? In the partition, in the quicksort?
The nature of the algorithm is splitting up the array into 2 parts and then sorting what's before the partition, what comes after the partition. If you keep doing that, it's similar to merge sort, I guess, a little bit.
Enachinami, but not 100%. Nachon that I'm dividing it up, but who says it's 2 equal parts?
Exactly, which is that its best case scenario turns to be n log n, but worst case scenario becomes n squared. If you have it in a reversed order and decreasing order, then you just end up doing everything n squared.
Okay, so here is a great example, and I promised that this in the beginning of the lesson when you asked about it, people. Here we're going to actually talk about worst case and best case. What is the worst case? The worst case here is that the array is already sorted. Let's say the array is already sorted, just for easiness. The array is already ordered in ascending order. So what's going to happen? Every time I take a pivot, every time I choose a pivot, on the left-hand side will be all the other values. I'm not going to split it up equally. So what's going to happen is that I'm going to have to do n, or n minus 1, plus n minus 2, n minus 3 times. When I'm going through that whole array to do all that swapping, the partitioning, the length, the amount of time I'm going to be spending is going to be n minus 1, n minus 2, n minus 3, which is n squared. But it's going to cost me a lot. So therefore, it's going to be really O of n squared in the worst case. And it makes no difference if it's sorted ascending or descending. The question is if it's on the left-hand side or the right-hand side. The average case, what's the average case? Average case means there's no particular order. I'm going to tell you that the complexity is n log n. I'm not going to prove it. To prove it, there's a lot of mathematics, quite heavy mathematics even. And because we don't know how to really evaluate a recursive function, it's harder for me to show it. If anybody particularly wants to see the actual nituach, I do have it in Hebrew, but most of it's mathematics anyway. You don't need the Hebrew too much. As a separate thing, I could put it in our area as well, and you could see the actual, really, somebody's really interested, or just look it up, try looking it up, but you need to know, you have to look at the mathematics of it, and it's not important for us. You can just take it that it's n log n. Now I'm asking you the question, what is the best case? What is the best case here? What's the case? When is the best case? When the array is what? When the array is, or when is the best case for running here? Question mark at the end of my sentence? Somebody?
Isn't it also n log n?
No, that will be the answer, but I want to know when does it happen? What's the hechatimsa? What's the hechatimsa of the best case scenario?
When the number you pick in the middle.
You're getting there, but do it more. The best case is that the array always splits equally. Means every time I take a pivot, every time it's gonna split it into two. Obviously it splits into two, but equal portions. If every time I split, it splits into two equal portions each time, then bemet I'll have log n.
Why? Because the partition is always going to be the same?
Yeah. The partition in each part, every time I take a partition, I choose the partition, it will split it down the middle.
Meaning we're keeping the partition as low as possible.
The amount of partitioning, yeah.
Yeah.
The amount of partitioning you want to, no. The amount of partitioning is going to be the same amount. It will be less, sorry. It will be less, definitely. Yes. So it's going to be n log n. Very nice. 2 points to mention. There are various methods to choose the pivots. I mentioned it beforehand. Basically, there are three main, there's a lot of studies and this way proves this way and that way, but basically there's three different ways you can choose the pivot. I can choose that the pivot is the right-hand value. You can also choose that it's the left-hand value. And now listen carefully. I can also choose a random pivot. I can make a random quicksort. I can say, you know what, let's just choose randomly, because the chance could be that it will be very nice. Every time I choose a pivot for that partition, I'll choose it randomly. Now, if I choose it randomly, it could be That would be very nice. Now, people do all these different researches and say this is good and that's good. A random pivot does sometimes work out very nice. So you do have that random quicksort capability, just for your information. And also, there are different ways to do the partitioning. We saw 2 different ways of doing partitioning. There's a couple of more algorithms that do the partitioning, but you're given a pivot, you have a pivot, and now, okay, let's see how we can partition it. 2 different ways, I mean, a few different ways, but there are different algorithms. You don't have to work with a specific algorithm. That was quicksort. So let's start summing up. Every recursive function has to contain a recursive call and the base case. We talked about different types of recursions: tail recursion, multiple recursion, co-recursion or mutual recursion. We talked about, hey, where is it? I'm supposed to say here, merge sort and quick sort. And if we want to really, really define, let's make a definition of recursion. A lot of people know what the definition of recursion is. Does anybody want to give us the definition?
The function calls itself.
See recursion. And Derech Hagav, try doing a Google on the word recursion. He'll say, do you mean recursion?
There's no base case in there.
I know, it's a joke. It's a, what you call it, it's the infinite recursion. Fine. So, okay. Chodesh Tov. Don't forget Yalav Yovel tonight. Bezrat Hashem, we'll meet next week. And next week, we're going to have a great time. We're going to be learning about trees. We'll learn how to climb trees. And we're going to have a really great time. It's a great topic, very important topic. And see you next week. Kol Tov.
Isn't there another?
Sorry?
Isn't there another case of recursion that it just bottoms out? In other words, you're multiplying by some number, and then at the end it doesn't have to pop all the way back up. Or someone explained to me once.
Yeah, I understand what you're saying. No, you have to pop up. It could be you're popping up straight away, but it's going to have to go through those steps, definitely, because that's the whole idea of the recursion. From what I know of, at least.
It would pop straight up if it's tail recursion?
Yeah, if it's tail recursion, basically it goes straight up, but it has those tachanot, it does have to go, it does return, but it doesn't do anything else in between. That's the whole point. There's no other commands after the return. Okay?
So if it has print, like in the early examples, print X or something after the call, it's not tail recursion?
Definitely not. Okay. All right. So, Shabbat Shalom, Chodesh Tov, and Bezrat Hashem, we will meet sometime. Sometime. Yes. Okay.
Thank you very much. Bye.
Thank you.
Bye.
Bye.
Very much.
Oh, I see people. Hello, Jonathan. At the end.
Thank you.
Okay.